atmospheric chemist, I think about the molecules we're breathing all the time. Like, if I'm around a forest fire, I'm thinking, oh, but what are the molecules and what is breathing? And look, the smoke's going this way and I wonder why. When I'm cooking, oh, what is the smell that I'm smelling? I'm using my nose as, my transportable instrument to think about some of these concepts. In my lab, we do atmospheric chemistry research. So essentially what that means is we want to know what molecules in the atmosphere, what they're doing. So we're interested in the molecules we're breathing. So every breath we take, is a cocktail of molecules we're breathing, but also what are these molecules doing for our climate and how that's changing, for example, with wildfire smoke and a changing climate. My name is Dr. Nadine Borduas-Dedekind, and I'm an assistant professor in the Department of Chemistry at the University of British Columbia. We are atmospheric chemists, and in my lab we're interested in understanding how organic molecules react in our atmosphere. And we have 4 teams in my group. We're interested in atmospheric ice nucleation, so how clouds form. We're interested in oxidants in the atmosphere, so how wildfire smoke produce oxidants. We're also interested in the organic molecules emitted by humans, and so the molecules that you put in through your deodorant this morning, for example. And lastly, how selenium, my new favorite element, travels through the atmosphere. We don't have beakers and solutions that we mix and look at, because we're looking at gases, we're looking at the atmosphere, and you can't pour the atmosphere. So what we do is we have instruments like what we call a smog chamber. So there's one that we built in my lab that's right behind me. It's 2 meters by 2 meters by 2 meters. And we can control very specifically which molecules are going in. And then we can shine light on our chamber to simulate sunlight and see how the chemistry is changing with the sunlight. We can also add oxidants like ozone and then see how the chemical transformations are changing the molecules in our bag. Sometimes our molecules are so reactive that we can measure them in smaller bags. And so this is another reaction flask for us to do our chemistry. And we take, for example, our mass spectrometer, and I call our mass spectrometer the super nose, because the way it works is it has basically a trunk, and you just point to what you want to smell, and it sucks in the air and ionizes it so that we can then guide it through some voltages and detect the molecules that are there. In atmospheric chemistry, there are 3 pillars to our science. We have fieldwork, we have modeling, and we have laboratory studies. And these really need to work together to understand how the molecules in our atmosphere are reacting. We can take our instruments to the field, discover a new molecule or a new process, and then we can take that information back into the lab and study it very fundamentally and systematically. And then we observe the lifetimes and the yields and the oxidation products, and then we can put that information into a model that's called a chemical transport model to then predict how these molecules are going to react.
So campaigns are usually short-term, often short-term, but very intensive. So they can range from, 1 week to 2 months. And so I have been on 3 different field campaigns now. One of my current projects is really looking at what kind of chemicals are emitted when we use fragrance personal care products, like perfume, for example. We found this group of compounds. They're called synthetic MOX compounds, and they are used in personal care products like perfumes and shampoos, but we found that they are also outside, and they peak in the morning. And so what this means is that when we use these fragrances inside our houses and we go out to work or places like that, we are actually transporting these compounds into the environment. What does this mean for our health? What does this mean for our climate? Since starting my PhD and working on perfumes and looking at just how these compounds influence our environment, my lifestyle has definitely changed by a lot. Nowadays, when I cook, I make sure my vent is on because I do not want to be inhaling all of those chemicals, like aldehydes and things like that. Also, a lot of the products I use, my body wash and body cream, is actually fragrance-free.
Overall, this is the environmental chamber. The idea is we're trying to create a system that will allow us to stimulate some sort of outdoor environment in a very extremely controlled setting. So this means we want to think about ways to control the temperature, create like a UV simulator or a solar simulator.
So this is a bag 2 meters by 2 meters by 2 meters. And we put all our molecules in there and we can study their reactions. But then we need to build the bag. So we use a lot of tools.
So we want to replicate the sunlight that is happening in the atmosphere inside the lab. So for doing that, we need this type of instruments where we have the same light, but in a small cube inside here. So if we put our sample inside, we have the same sunlight that is outside, inside here. So we have some collaborators in Europe because all the different lab has different instruments. So we are working all together to get to the same goal and to open the research and find the goals.
My study is on the topic of ice nucleation, so how ice formation essentially occurs. When I came into the lab, I first assumed that ice just froze at 0 Celsius, and I learned that that's not necessarily true. It's pure water freezes around -30 to 40 degrees Celsius, but you have these catalysts in the ice that cause freezing at warmer temperatures, such as near 0 Celsius degrees. One of these catalysts, I'll say, is a protein that comes from a bacteria called Pseudomonas syringae. And it's a really popular bacteria because it's the protein that it produces is used for artificial snow production. In one of my classes, Chem 211, which is analytical chemistry, I met my TA. His name was Paul. He gave my group a tour of the NBD lab, and I thought it was really cool. So I asked if I could try volunteering and getting to know their studies more. And yeah, he said, yeah.
So I'm interested in studying ice nucleation because I'm very much, I like to focus on the fundamentals of chemistry and physics. So my favorite lab equipment is actually our cryo microscope here next to me with a high-speed camera on top, because that allows us to really look into the process of freezing and to not only have the resolution of a microscope to see these tiny droplets much bigger, but also to make videos with really high time resolution to see how the crystals grow. So in this video you see a droplet at about -10 degrees Celsius, and then a protein within this droplet starts to trigger the formation of ice crystals. And so you can see the growth of the ice phase through this droplet as it gets initiated from this tiny little protein sitting at the air-water interface of the droplet. So within 50 milliseconds, this entire droplet is frozen. We would never see that in the video, but with our high-speed camera, we can actually time resolve this process and see how the ice crystals grow. So we conduct computer simulations in order to predict how often ice nucleation would happen at a certain location just by chance. And if the predictions tell us that it should be more distributed across the droplet than what we actually see, then we know that what we see cannot be just a randomly occurring event.
So my idea of research was that you had to have like a solid plan from the start, and you could complete a study within months from just doing one experiment and going to the next right away. But the reality is, it's a lot of troubleshooting. You do one experiment and then you find out that something went wrong or that you have some sort of unexpected result. So in a way, you end up doing a side study on something else to answer one of these unexpected results, and it ends up being not just one project, but one main project and several side projects. And I really like this because it allows me to study a lot of different things, which I find really interesting, all at the same time, instead of having to be tunnel visioned on like one specific aspect.
I think the very first thing you have to learn is to understand that it is a marathon and not a sprint. And essentially that means that you're not going to get it all at once. It is literally impossible. There will be a learning curve. And as long as you're willing to be interdependent, collaborate, talk to people, and be persistent, you will definitely get there.
So failure in research is really important. It happens all the time because we're essentially doing things for the first time in the entire world. No one's ever done the experiment that we're doing. And so it often doesn't work. And so a big part of research is perseverance. It's being okay with these failures and these mistakes. And this is really important to me because I make mistakes all the time. And so I put up these posters in my lab to really highlight that mistakes are expected. We inspect them, we correct them, and we respect these mistakes. But when we make a mistake, we actually learn a lot because we learn that our hypothesis needs to be revised and it's not working. And so that's when we learn the most, is when we fail.
The coolest thing about being a PhD student is that you can be curious and creative, and you can really think deeply about a certain question and about a certain result and spend as much time as you want to actually get to the answers that you want to have.
The best part of my job is working with my team. And I love that because we're learning every day. And there's no better job than learning something new every day. Yeah, my job's amazing.